Welcome to my YouTube channel dedicated to space. In this video we will talk about black holes and time warps, delving into astrophysical oddities. Black holes and time warps are among the most intriguing and mysterious subjects in the realm of astrophysics. These phenomena arise from the predictions of Albert Einstein's general theory of relativity, a theory of gravity that describes the warping of spacetime in the presence of mass and energy. Let's delve deeper into these astrophysical oddities. Black holes. A black hole stands as one of the most enigmatic entities in the universe. It's a region in space where the gravitational force is so potent that nothing, not even the fastest thing known to us, light, can escape its voracious pull. This seemingly impermeable boundary of a black hole is termed the event horizon. It acts as a point of no return. Any object or radiation crossing this threshold is inevitably drawn towards the central core of the black hole, known as the singularity. Within the singularity, our understanding of physics breaks down as densities spike to infinite values, challenging our comprehension of the cosmos. The birth of a black hole is a cosmic spectacle. The most prevalent method of their formation is the death throes of gargantuan stars. As these titanic stars deplete their nuclear fuel, they lose the crucial balance between the outwards push from nuclear reactions and the inexorable inward pull of gravity. This imbalance leads to a catastrophic gravitational collapse, condensing the star into a tiny, infinitely dense point, birthing a black hole. Black holes are not a monolithic entity but come in diverse sizes, largely determined by their mass. 1. Primordial black holes. These are hypothetical remnants from the universe's infancy. Conceived in the turbulent moments after the Big Bang, they are believed to have masses far less than that of a star, possibly as tiny as a single atom yet with the mass of a mountain. 2. Stellar black holes. As their name suggests, these are born from stars. More precisely, from the dramatic end of stars much more massive than our Sun. They typically contain up to 20 times the mass of our Sun but are confined within a region just about 10 miles in diameter. 3. Supermassive black holes. Lurking in the dark hearts of most galaxies, including our Milky Way, these colossal black holes possess masses ranging from millions to billions of solar masses. Their formation is still a topic of intense research, with theories suggesting they might result from the merger of several smaller black holes or the gravitational collapse of massive gas clouds in the early universe. Hawking radiation. Contrary to the moniker, black hole, these astrophysical behemoths are not entirely devoid of emission. The genius physicist, Stephen Hawking, postulated in 1974 that due to intricate quantum mechanical processes near the event horizon, black holes can radiate energy. This radiation, known as Hawking radiation, implies that black holes can, given sufficient time, evaporate, challenging the previously held notion of their eternal nature. Before continuing with the video, I remind you to subscribe to the channel and activate the bell, so you don't miss our videos on space. Time warps, or time dilation. One of the groundbreaking concepts to emerge from Einstein's theory of relativity is that time, contrary to our intuitive understanding, is not an absolute entity that flows uniformly throughout the universe. Instead, its passage varies based on factors like gravitational fields and relative velocities. This phenomenon, known as time dilation, suggests that time can elapse at different rates for people who are moving relative to one another. An astronaut traveling at a significant fraction of the speed of light in space, for instance, would age slower than his counterparts on Earth. Around black holes, the effects of time dilation become exceptionally pronounced in the vicinity of strong gravitational fields, such as those surrounding black holes. Imagine a spacecraft slowly approaching the event horizon of a black hole. To a distant observer, it would seem as though the spacecraft is frozen in time, endlessly inching towards but never quite reaching the event horizon. This is because, from the observer's perspective, time appears to slow down immensely for the spacecraft. Paradoxically, for the astronauts inside the spacecraft, time feels normal, and they would cross the event horizon in what feels like a regular span. This stark difference in perceived time is one of the most mind-bending aspects of relativity. Practical implications. Far from being a mere theoretical curiosity, time dilation has tangible effects that require real-world adjustments. Consider our satellite systems orbiting Earth. Due to their high velocities and their distance from Earth's gravitational pull, time ticks slightly differently for them compared to us on the surface. The Global Positioning System, GPS, which many of us rely on for navigation, is a prime example. If the effects of time dilation weren't accounted for, GPS satellites would relay inaccurate position data. In just one day, this discrepancy could amount to several kilometers, making the system practically useless. Hence, the onboard clocks on GPS satellites are fine-tuned to correct for this relativistic effect, ensuring the precision we've come to rely on. Wormholes. A wormhole paints a tantalizing image in both scientific and popular culture, a cosmic shortcut that bends the very fabric of spacetime. Conceptually known as the Einstein-Rosen bridge, a wormhole is not a hole in the traditional sense but rather a tunnel connecting two disparate points in spacetime. Theoretically, if one could traverse through a wormhole, they might be able to undertake what would otherwise be impossibly long journeys across the vast expanses of the universe within a blink of an eye. It would be akin to folding a piece of paper so that two distant points touch, and then piercing a hole through both. The mathematics of general relativity does permit the existence of wormholes. However, the challenges lie in their stability and traversability. Many theoretical wormholes, when bereft of any external support, would snap shut almost as soon as they form, trapping or annihilating anything attempting passage. This has led researchers to speculate on the role of exotic matter in stabilizing wormholes. This peculiar form of matter would possess negative energy density, countering the natural tendency of the wormhole to collapse. Yet, the nature, existence, and acquisition of such exotic matter remain subjects of intense debate and exploration. Potential applications and implications. The implications of a stable, traversable wormhole are profound. Interstellar travel, currently a distant dream given the vast distances and energy requirements, could become achievable. A journey between stars or even galaxies might be reduced from millions of years to mere moments. Furthermore, wormholes could offer invaluable insights into the earliest moments of our universe or even provide a glimpse into other possible universes. Challenges and unknowns. Beyond the issue of exotic matter, numerous challenges loom. Even if a stable wormhole were found or created, the journey through it could still be perilous. Gravitational forces might vary drastically within the wormhole, ripping apart anything that ventures in. There's also the question of where and when the other end of a wormhole might open. It could lead to a different era, a distant part of the universe, or potentially an entirely different universe altogether. In popular culture, wormholes have captivated our imagination, serving as central plot elements in numerous science fiction works. They've been depicted as portals for time travel, gateways to distant galaxies, or bridges to parallel universes. We'd love to know what you think. Comment below and don't forget to subscribe to the channel if you haven't already. We thank you for watching.